When you hear the words computer science algorithm, you probably picture like millions of cold logical switches just flipping on and off in the dark.
Oh, yeah. Very rigid, very unforgiving.
Exactly. But every now and then you peek under the hood of a really complex piece of software, and what you find isn't cold at all. It's almost organic.
Right. It behaves more like a living thing trying to adapt to its environment.
Yeah. You discover that the code relies on these beautiful physical metaphors like growing bubbles or expanding moats to solve seemingly impossible problems at lightning speed.
It completely flips your expectations, honestly. You go in looking for strict math, and you find geometry that feels alive.
And that biological organic math is exactly what we're dissecting today. Welcome to today's deep dive, where we have a really fascinating stack of sources in front of us.
We're looking at a technical presentation and some pretty dense documentation focused on a notoriously tricky mathematical puzzle.
Right, it's called Steiner Forest via Union Find and Primal-Dual, which
Wow.
I know sounds like a mouthful.
It definitely does. But we're also looking at how this is actively implemented right now in a Python software library called PhysDPy.
Exactly. And the mission for us today, for you listening, is to extract the mechanics from this documentation and figure out how software uses incredibly clever conceptual tricks to design the networks that basically power our world.
Because this specific problem really forms the backbone of modern physical design.
I mean, whether an engineer is trying to design the microscopic wiring inside a computer microchip or a telecom company is laying out a massive global fiber optic network across an ocean, they are ultimately dealing with this exact math.
You have points. You need to connect them, and you want to spend the absolute minimum amount of resources doing it.
Okay, let's unpack this. Before we get to the expanding modes in the software architecture, we have to define the beast we are trying to tame. Our sources refer to this broadly as the Steiner problem.
Right.
Imagine you're looking at a map of points connected by lines. In graph theory, this is an undirected graph. And those lines, or edges, have non-negative weights.
Which just means there's no such thing as a path that pays you to take it.
Exactly. For you listening, just think of the weight as the literal cost to build that connection. A longer, harder path costs more money. The fundamental goal is to connect specific points on this map for the lowest possible cost.
But the source material draws a critical distinction right away between a Steiner tree and a Steiner forest.
And those sound like interchangeable forestry metaphors, but they really aren't.
Not at all. Mathematically, they are entirely different animals with very different rules. A Steiner tree requires you to connect all of your terminal points into one massive single connected component.
Right, like every point must eventually have a path leading to every other point on the board.
Yes.
Reading through the documentation, the best way I could visualize a Steiner tree is to think of it like building a national interstate highway system. You're connecting every major city on a continent.
Everyone is on the exact same grid.
Right, sharing the same overarching infrastructure. But a Steiner forest, which is the focus of the PhysDPy algorithm we're looking at today, has a totally different requirement. It only asks you to connect case-specific pairs of terminals.
You're dealing with isolated pairs that have their own specific agendas.
Yeah, so my thought process here is that a Steiner forest is more like laying private, direct, highly secure fiber optic cables between specific corporate headquarters.
Oh, that's a great way to look at it.
Like Company A in New York only needs to talk to Company A in London. They do not care about Company B in Chicago trying to talk to Company B in Paris.
Right, they have no reason to interact.
Exactly. And if the cables from Company A don't ever need to cross or share a trench with the cables from Company B, they shouldn't. They can remain multiple, completely independent trees, hence a forest.
That perfectly captures the distinction. You're routing specific pairs, and you only share resources, like that physical trench for the cables, if it happens to mathematically be the absolute cheapest way to get both pairs to their respective destinations.
But wait, connecting just a few isolated corporate headquarters sounds vastly easier than connecting every single city on the continent to a massive highway system. If we just want to connect pairs, why is this considered so mathematically brutal?
Well, the flexibility of the forest is actually what creates the mathematical nightmare.
Really?
Yeah. Because the pairs don't have to connect to a central hub, the number of possible independent paths they could take is exactly so fast that even the world's most powerful supercomputers cannot brute force check every option to find the absolute minimum cost.
Wow.
An APX hard means we hit a hard mathematical wall. We don't just lack a perfect fast solution. It is mathematically proven that you cannot even guarantee getting arbitrarily close to the perfect solution efficiently.
So perfection is a literal impossibility if we want the answer in our lifetime. Which brings us to the central tension of the deep dive. If engineers can't calculate the perfect answer to lay out a microchip, how do they get a quote-unquote good enough answer, and how do they get it in fractions of a second?
Right, and that introduces the primary engine of the FISD's Pi software. It relies on something called the Primal-Dual approach.
And this is where the sources introduce the most fascinating visual concept in the entire stack of documents, the moat metaphor.
Yes, the moats. To get this incredibly fast, highly accurate approximation, the algorithm sets up two competing but linked mathematical realities. Think of a linear program as a set of mathematical rules trying to find a maximum or a minimum given certain constraints. First, you have the primal linear program.
And its entire existence is focused on minimization, right?
Exactly. It wants to select the absolute fewest, cheapest edges possible to connect the corporate headquarters.
I was thinking of the ultimate penny pinching accountant.
Mhm.
The primal LP looks at the map and wants to spend $0. It wants to select 0 edges.
That's a perfect analogy. But the accountant is forced to act by the other side of the equation. You have the dual linear program.
And the goal of the dual LP is maximization.
Right. It wants to maximize these mathematical values called dual variables. And the documentation visualizes these dual variables as physical, growing moats surrounding the terminal nodes that desperately need to be connected.
So imagine you're looking down at a vast grid, and the isolated corporate headquarters that need to connect are little castles. The algorithm starts growing these perfectly circular moats around the castles.
And the moats expand outward, claiming physical territory on the board.
What's fascinating here is how these two forces interact, right? The accountant and the moats.
Yes. What's fascinating here is the mechanism tying them together, which is a concept called complementary slackness.
Okay, complementary slackness. How does that work?
Think of the edges, the potential paths between the castles, as having a set capacity, almost like a progress bar. Every edge has a specific weight, a total cost. As the moats expand uniformly outward around the active components, which are the castles that haven't found their partner yet, the physical space of the moat starts overlapping these edges.
So the moats are essentially acting like water filling up a trench. They're filling up the progress bar of the edge's cost.
Exactly. And complementary slackness is the strict rule that an edge is only added to the final solution. It is only authorized and paid for by the penny pinching accountant when its dual constraint becomes tight.
Tight. Meaning what exactly?
In the physical metaphor, an edge becomes tight the exact moment that the expanding moats from either side physically touch and completely fill up the required cost of that edge.
Oh, wow. So instead of a computer just randomly testing billions of different paths, frantically checking spreadsheet values like a blindfolded person stumbling through a maze, the algorithm relies on this organic geometry.
It does. It forces the geometry to make the decisions.
It's like watching soap bubbles expand on a glass table. They grow larger and larger until they just barely overlap and snap, a connection is materialized. The moats literally force the most efficient paths to reveal themselves.
The geometry solves the problem organically. But, and there is a big but here, this organic growth creates a massive secondary problem.
I can imagine.
As these moats expand outward across a massive grid, and countless nodes start touching and snapping together, the map devolves into utter chaos.
Because things are just merging everywhere.
Right. You have individual castles merging into small islands, and those islands merge into massive continents. And those continents are still growing their own massive moats because somewhere inside them, a headquarters still hasn't connected to its specific partner.
That sounds like a memory nightmare. Tracking thousands of intersecting, expanding, constantly merging bubbles should absolutely crush a computer's memory. How does the software not just freeze trying to remember which point belongs to which massive, blob-like continent?
This is where the sources transition to the blue-collar machinery, making the elegant math possible. It's a data structure called union find, or disjoint set union.
Union find. So the Primal-Dual moats are the elegant theory, but union find is the workhorse operating under the hood.
Exactly. Its sole purpose is to instantly keep track of which individual points belong to which connected components at any given microsecond. And it manages this chaos using two incredibly clever optimizations.
Path compression and union by rank.
Yes. Let's look at the friction this solves. Normally, if you have a massive chain of connected points and you want to ask the computer, hey, who is the root node of this specific point.
The computer has to walk step by step up the entire chain to find the answer, which is incredibly slow.
Extremely slow.
The analogy that came to mind reading the sources was a massive corporate hierarchy. Like if an entry-level intern wants to know who the ultimate boss of their division is, they have to ask their manager, who asks the director, who asks the vice president, all the way up to the CEO.
And if thousands of nodes are doing that constantly as the moats merge, the system grinds to a halt.
Right, so path compression steps in and essentially says, the next time the intern asks who the boss is, once we find out it's the CEO, we are going to give that intern and every single manager in that chain the CEO's direct phone number.
Yes, it physically flattens the hierarchy.
Yeah.
The next time anyone needs to know who is in charge, the answer is instantaneous.
It permanently optimizes the path every single time a query is made.
And the second optimization, union by rank, prevents those deep chains from forming in the first place.
No, so?
When two of those massive moat continents finally touch and merge, union by rank ensures you always attach the smaller continent's root under the root of the larger continent. It keeps the overall depth of the hierarchy as shallow as mathematically possible.
That makes total sense. Now, I have to bring this up because the sources drop a detail about the time complexity for this union find structure that genuinely blew my mind. It notes that the time it takes to process these massive merges operates in O of alpha n time, where alpha n is the inverse Ackermann function.
Ah, yes, the Ackermann function.
The presentation slide brushes past this by just calling it practically constant, but we need to pause here because the math behind that is staggering.
It really is. The standard Ackermann function is famous in computer science for being one of the fastest growing mathematical functions ever discovered.
Right.
It scales so violently that computing it for even relatively small numbers results in values that far exceed the number of atoms in the observable universe.
Which is just, that's incomprehensible.
Mm-hmm.
But the algorithm uses the inverse of that function. Because the original function grows so unfathomably fast, the inverse Ackermann function grows slower than almost anything else in mathematics. If you ran this algorithm on a network containing as many nodes as there are stars in the universe, the inverse Ackermann function would still return a value of less than 5.
Which is wild to think about.
It's insane.
Yeah.
For all practical computing purposes in the history of human existence, it is a flat, constant number. It means the algorithm can merge these incredibly complex continents of lotes near instantaneously, completely independent of how massive the grid becomes.
It completely removes the tracking bottleneck. So the core loop of the algorithm is reduced to 3 lightning-fast steps executing over and over. Step 1, identify active components.
Meaning, ask union find which castles still need their partner.
Exactly. Step 2, ascend. Let the dual variables grow the moats uniformly until a new edge becomes tight. And step 3, select and prune. Use union find to instantly snap those newly touching points together.
And it just loops that process continuously until every target pair is satisfied.
Until everyone is connected.
So we have these beautiful soap bubble moats forcing connections and the near magical efficiency of union find keeping the computer from crashing. But here's where it gets really interesting. There is a glaring flaw in the moat growing process itself.
There is. When you let bubbles grow organically in every direction and force them to connect to whatever they touch, you inevitably overbuild.
Because the moats are blind.
Right.
They just expand until the requirement is met.
Right. They don't know if they're building the perfect path, they just know they're expanding.
Imagine the physical stakes for the listener here. You are an engineer laying down real physical infrastructure. Maybe it's titanium piping for an industrial plant or underwater fiber optics.
Very expensive stuff.
Very. If Company A and Company B's paths are growing toward each other, but they accidentally form a massive continuous loop before finally reaching their destinations, you have just wasted millions of dollars building a circular road that serves no purpose.
You can route data perfectly fine without the full circle.
Exactly. So how does the software detect and prune out those redundant cycles?
This initiates step 4 of the entire algorithm, reverse delete.
Reverse delete.
Yeah. The moment union find confirms that all of the target pairs share a root, meaning every corporate headquarters can successfully ping its partner, the moats immediately stop growing. The algorithmic phase shifts from building to pruning.
Okay, so it starts cleaning up.
Right. It takes the entire list of edges that the accountant paid for, and it iterates through that list backwards.
It walks back through its own history.
Exactly. It temporarily removes an edge, checks the union find structure to see if the terminal pairs can still talk to each other, and if they can, it realizes that edge was a redundant waste of money and permanently deletes it.
It cleans up the messy reality of organic growth. But, and this is my big question reading the source, why reverse order? If I'm cleaning up a mess, why does the direction matter?
It's a fair question.
Like, why not just randomly delete? If the computer just goes from the first edge added to the last, wouldn't it still find the useless loops?
The direction is actually the secret to the entire pruning phase. It relies on a deeply elegant mathematical guarantee regarding how cycles are formed. Think about a square made of 4 points.
Okay, 4 points.
If the motes build edge 1, then edge 2, then edge 3, those points are connected in a line, no redundancy yet.
Right, it's just a path.
But the moment the algorithm adds edge 4, it closes the square. A cycle is born. The documentation outlines the proof here. The last added edge in any cycle is always the mathematically redundant one.
Oh, because by the time edge 4 was added, a viable path edge 1, 2, and 3 already existed to connect those endpoints.
Exactly. The loop was unnecessary the second it closed. If you iterate through your edges in reverse order of addition, you are mathematically guaranteed to strike that redundant final piece of the cycle first.
That is so smart. By ripping it out immediately, you break the loop before you even evaluate the older foundational edges.
Yes, going in reverse guarantees you resolve into a strictly acyclic forest, a forest with 0 loops. And you do it without ever accidentally severing the crucial paths your target pairs rely on.
Man, that is elegant. We have the full architectural blueprint now. We have Primal-Dual motes organically discovering paths. We have Union Find, tracking billions of potential merges in microscopic fractions of a second using the inverse Ackermann function.
And we have a reverse delete, sweeping backward through history to prune out the expensive loops.
But, theory is just theory. When engineers actually run this through the FSD's software to design actual routing grids, does the organic math survive contact with reality?
It does, and the theoretical confidence in this algorithm relies on a famous 1995 theorem by mathematicians Agrawal, Klein, and Ravi.
The 1995 theorem.
Right. They proved unequivocally that this exact combination of primal dual and reverse delete is guaranteed to produce a forest with a cost no more than twice the optimal possible cost.
In the academic literature, I think it's written as the cost of F is less than or equal to 2 times OPT, a 2 approximation factor.
Yes.
So what does this all mean? Put yourself in the shoes of a lead engineer for a second. If I'm budgeting $100 million for physical routing material, and you proudly tell me your algorithm might cost me twice as much as the theoretical perfect layout, I'm finding a new algorithm.
You'd be pretty mad.
100% margin of error doesn't sound very impressive if you're paying for actual routing material. Is 2x really the standard?
It sounds alarming until you separate the theoretical structural limit from the empirically observed behavior. The type factor of 2 is an absolute worst-case mathematical upper bound.
Okay. The worst case.
Right. The proof of that boundary relies on the geometry of what we just discussed, the acyclic forest. After the reverse delete step, you are left with a graph containing absolutely no loops. And in any acyclic forest, there is a hard geometric law that the sum of the degrees, the total number of connections coming off all the vertices, is strictly less than or equal to 2 times the number of vertices.
The math literally cannot exceed that ratio because the physical structure of a tree prevents it.
Exactly. It is the ceiling of failure. But the sources provide incredibly detailed experimental validation data from the FSD's Pi test suite, and the practical story is vastly different.
Different how?
Well, while the theoretical ceiling is 2, the worst observed ratio across their stress tests is actually hovering around 1.269.
Oh, wow. That's radically different. That is incredibly close to the theoretical, incalculable optimum.
Highly near optimal, and the efficiency gains are staggering. When developers pit the Primal-Dual Steiner forest or PDSF against other standard industry methods like greedy heuristics or randomized approaches, PDSF isn't just more structurally accurate, it executes 1 to 3 orders of magnitude faster.
1 to 3 orders of magnitude.
Yes, and more importantly, its runtime scales completely independently of the terminal count. You can flood the map with hundreds of isolated corporate headquarters that need connecting, and the algorithm maintains its speed.
That's incredible. The large-scale benchmark test in the presentation really anchored the sheer power of this for me. They simulated a 20 by 20 routing grid. That is 400 total nodes, simulating a highly complex microchip surface. And they challenged the algorithm to connect 150 independent terminal pairs simultaneously.
That level of density is a massive routing headache. The paths are essentially fighting each other for physical space.
And the algorithm mapped it flawlessly with a total routing cost of just 233.0. It densely routed all 150 pairs, dodging and weaving them through the grid by strategically inserting only 27 minimal Steiner nodes.
Those are the extra non-terminal junction points the moats discovered just to combine the cheapest paths.
Right. If you look at the visualization of that test grid in the source, it is this staggeringly complex interwoven network of blue, red, and green dots. And the code solved it by just letting the bubbles grow.
It is the ultimate proof of concept. The fusion of the Primal-Dual abstraction with the hyper-efficient union-fine architecture creates a tool that doesn't just work on a professor's whiteboard. It works inside the actual software engines driving physical design today.
It's just a remarkable journey. I mean, for you listening, we started with the impossibly dense APX hard problem of routing Steiner forests, a problem that mathematically forbids a perfect shortcut.
Yep.
We navigated it by abandoning rigid calculation, opting instead to let mathematical moats grow and compete for space. We tracked those sprawling continents of data with the reality-bending speed of the inverse Ackermann function, and we brought order to the chaos by walking backward in time to delete redundant loops.
And the most exciting part is that the documentation emphasizes this is not a finished project. The developers actively maintaining FSD's Pi are expanding the architecture right now.
What are they adding?
They are adding support for diagonal edge routing, generalizing the mathematics to operate in fully 3D grid environments, and building direct integrations with global routers to transition the math straight into hardware manufacturing.
So the tool is alive, and it is evolving. Which actually brings me to a final thought I want to leave you with, based on a tiny note hidden in the open problems section of our sources.
Oh, the Bykowski paper.
Yes. We talk about how for nearly 30 years, since Agrawal, Klein, and Ravi published their proof in 1995, that approximation ratio is stuck at exactly 2. It was treated as a fundamental theoretical wall in computer science.
And an unbreakable boundary.
But the sources casually note that recently, in 2024, a team of researchers, Bykowski and their colleagues, finally beat it. They broke the 30-year wall.
They did.
But they didn't break it by a massive leap. They published a paper achieving a new approximation ratio of 2 minus 10 to the power of negative 11.
100 billionth.
They shaved 100 billionth off the margin of error just to prove it could be done. Which leaves you to ponder, what does it take for human mathematicians to scrape together enough insight over 3 decades to break a foundational barrier by such an unimaginably microscopic fraction?
It's a huge achievement.
It is, and more importantly for the engineers actually building the future in the quest for optimization, at what exact point does theoretical absolute perfection stop mattering to practical engineering? Because as we thought today, sometimes the smartest way to solve the hardest problems isn't to brute force the perfect math. Sometimes the best solution is to just set up the rules, sit back, and let the moats grow.